All right, so in section 3, we're not looking at proportions, we're looking at means. Now, there's two different ways to look at means as independent samples or dependent samples. In section 3, we're going to be looking at independent samples. Um, if we were looking at the mean of ounces in Coca-Cola and Pepsi in their 2-liter bottles, um, I could do 15 from Coca-Cola and 20 from Pepsi, or I could even do 15 from Pepsi, but there's not something that's tying them together. These are just different types of sodas. I want to look at the means to see if the numbers of ounces are roughly the same, or are they statistically different. And that's an example of an independent um, group, populations, samples. If I was doing something dependent, which would be section 4, that's kind of when you're looking at, let's say if we say that people marry within their IQ. So you would have a man's IQ and a woman's IQ, right? And so would they be paired up the same? So I guess I should say spouse. Um, so if you have your first partner married to the second partner, they're married. Those are the two that you want to compare. I just don't want to look at an average of all the men's and then um, or all the first partners and then all the second partners. I'd want to compare the differences between the first person and who they're married to, the second person. So that we'll talk about more in section 4, but right now these are independent samples. So one group doesn't necessarily, they don't depend on the second group. So if I'm looking at this one, researchers conducted a study to determine whether magnets are effective in treating back pain. The results are shown in the table for treatment and without treatment. And so we get these different means. Reduction in back pain. So was there reduction in back pain? So this one looks like it has more than this one, but is it significantly more? That's what we have to determine. Is it significantly more? So if we were doing our null hypothesis, do not assume that the population standard deviations are equal. We'll talk about that in a second. Test the claim that those treated with magnets have a greater mean reduction in pain than those given a sham treatment. So our null is always that they're equal to each other. And then we think this one is going to be bigger than this one, right? Because they said is greater, have a greater mean. So that's reading the context. The test statistic, well, I'm going to use StatCrunch to figure that out. Make sure we still can see our data. But I am looking at a t-stat, and it's a two sample. In section 4, we'll be looking at paired, dependent, and in section 3, we are two sample, and I just have a summary of the data. My mean for the treatment group is 0.5152. Standard deviation is 0.74, and the sample size was 19. For the sham, the placebo, 0.42 with a standard deviation of 1.13 and a sample size of 19. Uncheck this box. Unless they tell us that we believe that the variances are equal, we will uncheck that box. And I think we did say that it would be greater than. Again, notice the difference. If saying that they're equal to each other, the same thing as saying that the difference is 0. And the first one greater than the second also means that if you subtract them, you'd get a positive number, something larger than 0. So we put all our information in, we uncheck this box because it says do not assume they are equal, so we will uncheck that box and hit compute, and we get a test statistic and our p-value. So our test statistic to 2 decimal places is 0.32, and our p-value is 0.375 to 3 decimal places. So this is larger than our alpha. So we would fail to reject the null hypothesis, and there is not sufficient evidence to support the claim. So more words. Is it valid to argue that magnets might appear to be effective if the sample sizes are larger? Since the let's see. Is it valid to argue that magnets might appear to be effective if the sample sizes are larger, if we had larger sample sizes? Since the sample standard deviation for those treated with magnets is less than is greater than the sample may is given a sham treatment, it is valid to argue that magnets might appear to be more effective if the sample sizes are larger. So this is looking at sample sizes. Let's check that. Good. That was hard to read. Making a confidence interval. So we had an alpha of 5%. So if we were going to use a confidence interval, it would be a 95%. And then here are those bounds to 3 decimal places. Negative 0.532 and positive 0.732. Again, 0 is in here, so that's why we assume that there's no differences, right? Oh. A greater mean reduction, so just not different, but a greater mean reduction. So what I think I would have to do here, is if I want 5% to be in one tail, I think I would make this a 90%. 5% to be in one tail. We're going to try this out. Because again, that would be 5% to the left, 5% to the right would be a 90%. Not thinking that this is going to be right though. Those treated with magnets have a greater mean reduction in pain than those given a sham. Let's try this. Not necessarily certain that this is 425, 625. I don't think this would be right either. Oh, it is right. So since our alpha was 5%, and we were looking at one tail, we would have to change that to 90%, because if you think of your normal curve, or our T curve, whichever we're looking at, if I'm just at 5%, right, that gives me 2.5 over here and 2.5 over here. But if I want 5% on both sides, that would give me this 90%. So since I'm just looking at the one side, we would have to make that a 90% problem. One other one to look at real quick, just to show how it's set up, is number 6. And so in number 6, they give us data. So everything else would be done similarly, but again, notice that it's not the same numbers, the same sample sizes. They're different sample sizes. But we could go in here and we could do a stat tstat to sample with data. And we just have to draw archbishops first and then monarchs second. Again, unless they tell us that it's the standard deviations are equivalent, we will uncheck this. So typically we will uncheck this. Here would be one just to show that they're not equal to. Over here it looks like it says less than, so we can make it match. But when you compute, you'll have your test statistic and you'll have your p-value.